Very good morning, students. Myself Narendra A, lecturer, Government Polytechnic Chintamani. As you all know, today is it's my third session. In the last class, we discussed about many theoretical concepts like stress strain behavior of a mild steel and stress strain behavior of a glass and stones, and many examples I have given. And I have discussed about the elastic constants. In the last class, I have started with a simple problem on stress, strain and elongations. Today also in this class also I will use to continue the same topics and problems on same topic. So that take down is the next problem. A problem given as a short column has an internal diameter of 200 mm full stop. What would be the minimum external diameter so that it may carry a load of 1600 kilonewton with a factor of safety of 5. Here given as ultimate stress of steel is 472 Newton per millimeter square. Here what the question is, here they are given as a load given as a 1600 kilonewton. So that we have to design an alloy column so that internal diameter and external diameter should be, internal diameter is given here. We have to calculate external diameter such that external diameter should resist the load coming on that. So that here given as only here given data is internal diameter is given and the load is given, factor of safety is given and ultimate stress is given. So that here it is like a design problem. So that we have to design what is an external diameter so that to resist the load coming on the that were given to a given load, they have to resist the given load. That's all. So that first down we make note the given data here. Given data internal diameter as 200 mm and load given P as 1600 kilonewton. Ultimate stress is given, it's very important. Ultimate stress is 472 Newton per millimeter square ultimate stress, and given factor of safety as 5. Here given factor of safety as 5. So that here we need to calculate what is the external diameter. Here we need to calculate external diameter. External diameter may be noted as a capital D, is the question mark. Our intention is to find out what is the external diameter. So that the question before starting the problem, we have to think how the external diameter will come. For an alloy tube or for a short column, for a column alloy tube, it is alloy tube. We have to calculate, we have to know the formula for an area. Suppose this is the column, this is the column, this is the column, this is the internal diameter small d, this is the internal diameter small d, this is the external diameter capital D. This is the external diameter capital D. This is the internal diameter, this is the external diameter we need to calculate. This smaller d as given. See, this capital D will get only in terms of area, If you write a formula for this column, see pi d square minus small d square, pi by 4. Even for area for a circular section is pi d square by 4, because it's an alloy. We have to minus from larger area. We are larger diameter in smaller diameter. We have to minus smaller diameter in larger diameter, so that we will get external diameter only in area. So that we need to find out what is an area. So that here given as an ultimate stress and factor of safety is given. So that area where we will get in stress. Stress is equal to load by area. We will get area only in the stress formula. Stress is nothing but which stress it is. It is, I am telling you, in most of the problem, on all the cases we use working stress. This stress is working stress. So that if you calculate working stress, we will get an area. If you calculate an area, we will get diameter. If you calculate a working stress, we will get an area. If you calculate an area, we will get diameter. So that here ultimate stress is given. So factor of ultimate stress is given and factor of safety is given. factor of safety as a 5 and ultimate stress is 472 Newton per millimeter square. We have formula factor of safety is equal to ultimate stress divided by working stress. US means ultimate stress, working stress means WS. We have factor of safety as 5, it is a given. We have factor of safety as 5 and ultimate stress is 472 Newton per millimeter square. 472 Newton per millimeter square. Our intention is to calculate what is working stress. What is working stress? Now working stress is equal to 5 into 472. Working stress is equal to 5 into 472. We will get working stress F is equal to 472 divided by 5. We will get working stress is equal to 94.4 Newton per millimeter square. This is the working stress. F is equal to 94.4 Newton per millimeter square. This is the working stress we need to calculate. So that after I told already, if we got the working stress, we can calculate what is the area, because we have F is equal to load by area. We have F is equal to stress is equal to load divided by area. Here load is given, load is P is equal to 1600 kilonewton. Load is given here. We know the load and we know the stress. So that by using this relation, we can calculate what is an area. So that area is equal to P by F. Area is equal to P by F. So that P is 1600 kilonewton. We can convert that into Newton. So that 1600 into 10 to the power of 3 divided by area 94.4. This is the stress, this is the load. If you simplify this, we will get area as 16949.15 millimeter square. This is the area required. To resist the load of 1600 kilonewton. This much of area is required to resist the load of 1600 kilonewton. So if you know this area, here an internal diameter is given. So that area is equal to area of a alloy section is area is equal to pi by 4 external diameter square minus internal diameter, pi by 4 into capital D square minus small d square. Capital D square minus small d square. Here small d is given. So that we know area is equal to 16949.15 is equal to pi by 4 is equal to, we have to calculate what is capital D. Here we know we have to calculate what is capital D. So that D square is equal to 200 square. So that by doing simplification, we will get 16949.15 is equal to 0.786 into D square minus 200 square. If you substitute pi is equal to 3.14, we will get 3.14 divided by 4 will get us 0.786. By doing simplification, we will get D square is equal to 21563.8 plus, if you take this minus 200 square to this side, we will get as 40,000. We will get it as 40,000. So that D, we will get D is equal to 248.18. 248.12 mm is the external diameter required to resist the load of 1600 kilonewton. Our intention is to calculate is only the external diameter. First we are calculated what is the working stress. By using that working stress we are calculated what is an area. By using that area we are calculate what is the external diameter required for to resist that load. So this is the problem. So next we can take it as the next problem. You can take the next problem. So here also I have taken the same type of problem here. Hollow steel tube of an external diameter 1 or 2 mm is to be used to lift a load of 140 kilonewton. The yield stress is 250 Newton per millimeter square and a factor of safety is 1.75. What is the inner diameter? Here what is the inner diameter? See, the difference between that problem and this problem is, here directly working stress is given. Here directly working stress is given. We need to find out only what is the, here need to find out what is the only internal diameter. Here external diameter is given. We need to find out what is the internal diameter. You need to find out what is the internal diameter. Same type of problem this, you can solve it by your own yourself. So that here directly working stress is given, so that here one factor of safety is given as an extra, that's all. Here no need to, actually it is no need, not necessary it is a factor of safety, because yield stress is directly given. Yield stress is nothing but it is working stress only. If ultimate stress is given, we need factor of safety. Here yield stress is directly given, so no need of factor of safety. So that directly we can calculate here. We can directly working stress is given, so that working stress is equal to 250 Newton per millimeter square. 250 millimeters working stress is directly given. If you do F is equal to load by area, we know what is the load here. Load is equal to P is equal to 140 into 10 to the power of 3 Newton per millimeter square. 143 Newton. 140 into 10 to the power of 3 Newton. P is given, so that we need to calculate only area here. A is equal to same type of problem, so that we can do P by F. We know F, we know P, we will get an area. So that by using an area, A is equal to pi by 4 into capital D square minus small d square. Here we need to calculate only small d. Here if you substitute this area in this equation, we will get small d. So you will get an answer here. So thus here another problem is given here. Here another problem is given here. So that a steel bar of 50 mm, a steel bar of 50 mm by 50 mm in section, a steel bar of 50 mm by 50 mm in section is 1.2 meter long. It is subjected to an axial pull of 200 kilonewton. What are the change in length, width and volume of the bar if the value of 1 by m, that is Poisson's ratio, is 0.3, take E is equal to 200 GPa. This is one of the important problems, so that we can solve here. Here it's a here one bar as a cross section of 50 mm by 50 mm in a section, and it has 1.2 meter length. It is subjected to an axial pull. We are applying an axial pull of 200 kilonewton. We are applying an axial pull of 200 kilonewton. What are the change in length, width and volume of the bar? So that here when load is applied on the body, so that it changes in all the directions. I already said while telling the theory, if you apply load at one section, at one direction, so that changes will occur in all the directions, all the three directions. So that in this problem we have to calculate what are the changes in all the directions. First we have to note down the data. Here given cross sectional details are given, so that this is the bar of cross section 50 mm by 50 mm, 50 mm by 50 mm, 50 mm by 50 mm. So that I mean 50 mm by given B is equal to 50 mm, small t is equal to 50 mm. Here given as a rectangular bar, it is not a circular bar, it is given as a rectangular bar. So here given both the B and T, and we have length is equal to 1.2 meters, that is 1200 millimeters. 1200 millimeters. We given P is equal to 200 kilonewton. So that 200 into 10 to the power of 3 Newton. 200 into 10 to the power of 3 Newton, and given 1 by m. This is Poisson's ratio. We can call it as a mu. Poisson's ratio mu is equal to 0.3. Here given 1 by m is equal to mu is equal to 0.3, and given here E is equal to 200 into 10 to the power of 3 Newton per millimeter square. See, here given E is equal to 200 GPa. Here given E as a 200 GPa. So GPa means gigapascal. So that 200 into 10 to the power of 9 Newton per meter square. Newton per meter square. This is the here given 200 GPa. So that here we are converted all the units to millimeter. Here we are converted all the units to millimeter. So that here also we are converting this meter square into millimeter square. So that 200 into 10 to the power of 9 into 10 to the power of minus 6 Newton per millimeter square. We are converting this meter square to millimeter square. It's in denominator. If it comes up, it becomes minus. So that 200 into 10 to the power of 9 into 10 to the power of minus 6. So that finally we will get 200 into 10 to the power of 3 Newton per millimeter square. 200 into 10 to the power of 3 Newton per millimeter square. So next, this is the given data here. It is the given data here. So that before coming to the point, here we given the both the B and T are given, so that we can calculate here. See, any cases I told already, for calculating volumetric strain and all, we need to calculate what is an Young's modulus, and we need to calculate what is the lateral strain and what is the change in depth. So that here for calculating this, we know what is an Young's modulus here. Here we know what is an Young's modulus. Here value of Young's modulus is known. And another point is, here first of all we need to calculate what is the strain. Here first of all we have to calculate what is the strain required. So that for the requirement of a strain, we need to calculate what is stress. Because Young's modulus is equal to stress by strain. Young's modulus E is equal to stress by strain. Young's modulus is equal to stress by strain. So our intention is to calculate what is the strain. So for calculation of a strain, we need what is the stress. Required. So that stress is equal to, as we all know, stress is equal to load by area. Stress is equal to load by area. So that F is equal to, we know load is equal to 200 into 10 to the power of 3. We know stress is equal to 200 into 10 to the power of 3, and area of cross section is given. B and T are given here. So that area is equal to 50 into 50. 50 into 50. We will get stress is equal to 80 Newton per millimeter square. We get stress as 80 Newton per millimeter square. Now we know what is the stress. We know the value of a stress, and we know what is the Young's modulus. So that by using the stress and Young's modulus, we can calculate what is the strain. So that Young's modulus is equal to stress by strain. Young's modulus is equal to stress by strain. So that we need strain. So that stress divided by Young's modulus. Strain is equal to stress divided by Young's modulus. We have stress is equal to 80. And we have Young's modulus is equal to 200 into 10 to the power of 3. 80 divided by 200 into 10 to the power of 3. We know 80 divided by 200 into 10 to the power of 3. If you simplify this, we will get strain E is equal to 4 into 10 to the power of minus 4. We will get strain E is equal to 4 into 10 to the power of minus 4. This is the strain. 4 into 10 to the power of minus 4. So that after getting the strain, see, after getting the strain, we need to after getting the strain. This strain what we got is it is a longitudinal strain. The strain what we got now is longitudinal strain, because we are taken load. We are calculated along the length. We are calculated along the load applied. So that what we got is it is a longitudinal load, longitudinal strain. So that elongation delta L. Elongation, we need to calculate what is elongation delta L. We need to find out it is the elongation along the length. It is the changing along the length. I mean the changes along the length. How much of length is changing along the length? So that we have E is equal to delta L by L. We have E is equal to delta L by L. This strain is longitudinal strain. This strain is longitudinal strain. So that E is equal to delta L by L. So delta L is equal to E into small l. Delta L is equal to E into small l. So that delta L is equal to, we know E is equal to 4 into 10 to the power of minus 4. E is equal to 4 into 10 to the power of minus 4, and the length, and we know length is given as 1200 mm. 1200 mm. We will get delta L as 0.48 mm. 0.48 mm. This means that 0.48 mm is changing along the length. Delta L is nothing but it changes occurring along the length. So that here we got one changes. Actually our intention is to find out what is the changing along the length, along the breadth and along the thickness. So that here we got 1 unit. Here we have calculated what is the changes occurring along the length. Okay, then coming to the next point, so that we have to find out what is the changing in the breadth and changing in the thickness. In the next so in the next phase, we need to find out. Now see, we have calculated this. Here we have calculated the changes along the length. So that we need to find out what are the changes. We need to find out what are the changes along the breadth and the thickness. Here we have to calculate what are the changes occurring the breadth and thickness. So that here we have to calculate what is the lateral strain. That's very important. I already said in that case, in delta L case, we are taken as a longitudinal strain, because we are applied along the direction. We are applied along the length. We are applied the load along the length. So that is the longitudinal strain. So now here we have to calculate what is the lateral strain. That's why the value of Poisson's ratio here given. So that lateral strain is equal to, so that we know that Poisson's ratio 1 by m is equal to lateral strain by longitudinal strain. Lateral strain by longitudinal strain. Here given 1 by m is equal to lateral strain by longitudinal strain. We know the value of longitudinal strain. And we know the value of Poisson's ratio. We know the value of Poisson's ratio and we know the longitudinal strain. So that by using these two values, we can calculate what is lateral strain. So lateral strain is equal to 1 by m into longitudinal strain. 1 by m into longitudinal strain. So that here we get it as, we know Poisson's ratio is 0.3. If you multiply by longitudinal strain, we will get 4 into 10 to the power of minus 4. 4 into 10 to the power of minus 4. We will get it as 1.2 into 10 to the power of minus 4. We will get 1.2 into 10 to the power of minus 4. This is the lateral strain. lateral strain, this lateral strain means this is the changes going on other perpendicular direction of load applied. Strain occurring along the perpendicular direction of the applied load. This is the lateral strain. So that by using lateral strain we can calculate what is the change in breadth. So here you have to calculate what is the change in breadth. So that next step you have to find out change in breadth. Change in breadth. Lateral strain is equal to delta B by small d, delta B by small d, because B is exactly perpendicular to the application of the load. B is exactly perpendicular to the application of load. So here B change in breadth, it comes under lateral strain. So that here lateral we have to calculate what is lateral strain. Here delta P is equal to lateral strain into capital B, small b. So lateral strain, we have lateral strain is equal to 1.2 into 10 to the power of minus 4 into 50. We will get it as 6 into 10 to the power of minus 3 mm. 6 into 10 to the power of minus 3. This is the change in breadth. This is the change in breadth. What we required now. This is the change in breadth what we required. So this is the change in breadth. So that another question here we asked is, you have to calculate what is the change in volume. What is here? Another question is change in volume. Change in volume. Already have a given formula. I have given formula for an volumetric section, volumetric strain for a rectangular section. For a rectangular section, EV is equal to E into 1 minus 2 by M. EV is equal to E into 1 minus 2 divided by M. This is the volumetric strain for a rectangular section. If we substitute these values, so we have E is equal, where V is the longitudinal strain, so that E is equal to 4 into 10 to the power of minus 4 into 1 minus 2 into 0.3. EV is equal to 4 into 10 to the power of minus 3 into 1 minus 2 into 0.3. Here 1 by m is given as a 0.3, so we are directly write 2 into 10 to the power of 2 into 0.3. So we will get it as 1.6 into 10 to the power of minus 4. Here EV is equal to 1.6 into 10 to the power of minus 4. We know change in volume is equal to EV is equal to delta V by V. EV is equal to delta V by capital V. So our intention is to find out what is delta V. Here we have to find out what is the total change in volume. Delta V is equal to capital V into EV. Here gets in a volume, so that here we will get V as length as 1200 and breadth 50 and thickness 50. So that get V is equal to here 3 into 10 to the power of 6 millimeter cube. Length into breadth into thickness. Is the volume. So that if you multiply by three values, we will get V is equal to 3 into 10 to the power of 6 millimeter cube. So if you substitute these values, 3 into 10 to the power of 6 into EV as 1.6 into 10 to the power of minus 4, we will get it as change in volume as 480 millimeter cube. 480 millimeter cube. See, basically first what we started here, our intention is to find out what is the change in length, and we need to find out what is the change in breadth, and next finally we calculated what is the change in volume. So that for changing we need to calculate, if you calculate the changes, we need to calculate what is the longitudinal strain. First we calculated longitudinal strain, so that afterwards by using this longitudinal strain we need calculated what is the change in length. After that we calculated what is the lateral strain, so that after calculating the lateral strain we need calculated what is change in breadth. So after that we calculated what is the change in volume. So that the next problem we can take it as, a rectangular bar of 100 mm, a rectangular bar of 100 mm by 50 mm by 40 mm is subjected to 100 mm See, a rectangular bar of 100 mm by 50 mm by 40 mm long is subjected to an axial pull of 200 kilonewton if the Poisson's ratio is 0.3 and E is 10 to the power of 5 kilonewton. So in here given rectangular bar as 100 mm by 50 mm by 40 mm long is subjected to an axial pull of 250 kilonewton if the Poisson's ratio is 0.3 and E is 2 into 10 to the power of 5. Find what is the change in length, change in width and thickness and change in volume. See, in this problem also it is the same case. In the same case, here also given as a Poisson's ratio, here also given as a Poisson's ratio as well as a Young's modulus. So that in this case, here given B is equal to 50 mm, T is equal to 40 mm, and load given as 250 into 10 to the power of 3 Newton. 250. Problems on bars of varying cross section and principle of superposition. I already discussed in the last class how to solve the problems on a bars of varying cross section and as well as the principle of superposition. So that by using that concept, now we can solve the problems of varying cross section. Here given as one problem, a steel bar of 700 mm long, for its first 200 mm it is 25 mm diameter. For the next 300 mm it is as 20 mm in diameter, and the remaining 200 mm it has 15 mm diameter. So that here 3 diameters are given and 3 lengths are given. So it's gradually decreasing. By seeing problem we can say that it's a gradually decrease in diameter. So that here we need to find out what is the change in length if it is subjected to an actual tensile load of 100 kilonewton. We need to find out what is the change in length if it is subjected to 100 kilonewton, and also we have to find out what is the strain energy stored in this bar, and also we have to find out here what is the strain energy stored in the bar. Here we can given as an Young's modulus E is equal to 2.1 into 10 to the power of 5 Newton per millimeter square. So that here need to find out what is the total change in length. Here we need to find out what is the total change in length. So that before starting of the problem, here we have to write the given we need to write what is the given dimension, given data. So that here given as first here given as a steel bar of 700 mm long. That means that total length of the bar is 700 mm. For the first 200 mm it is 25 mm diameter. That means that L1 is equal to 200 mm. L1 is equal to 200 mm. L1 is equal to 200 mm. For that given L1, diameter D1 is 25 mm. For the given length L1 is equal to 200 mm. For the given for this stretch the diameter is 25 mm. We have to see the next step in the problem. For the next 300 mm, 20 mm is in diameter. For the next means that is L2 is 300 mm. L2 is 300 mm and diameter D2 is 20 mm. And diameter D2 is 20 mm. Diameter D2 is 20 mm. And the remaining 200 mm, that's because total length, capital length is given as 700 mm. Total length is given as 700 mm. So the first stretch is 200 mm, second stretch is 300 mm, and the third stretch is remaining 200 mm. And the remaining diameter is the diameter for remaining length is 15 mm. 15 mm. So that for this given data we have to write the sketch. We have to write the sketch, because if you write the sketch it is very easy to analyze. So that the first stretch is 25 mm diameter. 25 mm diameter. 25 mm diameter. 25 mm diameter. So that next stretch is for a stretch of 300 mm. For the remaining stretch diameter is 20 mm. Again it's gradually decreasing. Here see 3 dimensions. See here length first stretch is for here first stretch is it is given as 200 mm. 200 mm. So second stretch is 300 mm. 300 mm. So the third stretch is 200 mm. See diameter of the length, this one is 20 mm. This is 25 mm diameter. 25 mm diameter. For this section the diameter is 20 mm. 20 mm is the diameter. For this stretch the diameter is 15 mm. 15. See here diameter is gradually decreasing. This is the best example bar sections of varying cross section. It is a section for varying cross section. So that here 25 mm is the diameter, 20 mm is the diameter, and 15 mm is diameter. So that particularly we are applying an actual full of 100 kilonewton. In the problem it is given we are applying an actual full of 100 kilonewton. We are applying an actual full of 100 kilonewton. We are applying actual full of 100 kilonewton. So here actually it is a problem. It is a problem given actually. We have to write the sketch by reading the problem. So that by using the given data we need to find out what is the change in length. We need to find out what is the total change in length due to applied load in all the cross section. So actually what the principle of superposition says. So according to the principle of superposition we know that delta L is equal to small delta 1 plus small delta 2 plus small delta L3. That means total change in length is equal to change in length is summation of all the change in length in all the cross sections. So that capital delta L is equal to small delta 1 plus small delta L2 and small delta L3. Small delta 1 is the change in length in this cross section. This this is section 1, this is section 2, this is section 3. This is delta 1 is the change in length in section 1, delta L2 is the change in length in section 2, delta L3 is the change in length along the section 3. We know that delta L1 is equal to PL1 by AE. Here material is same. Here the material we are using is same, so that the value of Young's modulus remains same for all the values, and we are using different cross section, but so that here area of cross section changes. So that P1 L1 P2 L2 by A2 E plus P3 L3 A3 E. So this is the change in length we have to find out. Here we are applying at the ends, so that here P1 is equal to P2 is equal to P3 is equal to P is equal to 100 into 10 to the power of 3 Newton. P1 is equal to P2 is equal to P3 is equal to P is equal to 100 into 10 to the power of 3 Newton. So that here we have to calculate, here we know what is a L1. Here we know what is a L1, we know what is a L2, and we know what is a L3. We know what is the Young's modulus, and we know the value of P. Now we need to calculate what is an A1, A2, A3. A1 is the area of cross section in section 1. Area of cross section in section 1, that is diameter is 25, pi into 25 square pi d square divided by 4. Pi into 25 square divided by 4, we will get area as 490.87 millimeter square. 490.87 millimeter square area of cross section 1. A2 is equal to pi into 20 square divided by 4. This is the area in section 2. This is area in section 2. We will get it as 314.16 millimeter square. 314.16 millimeter square, it is the area for cross section 2. This is A3. This is 5 into 15 square divided by 4. We will get it as area here 176.71 millimeter square. 176.71 millimeter square. This is the different areas for different cross sections. If we substitute these values in this formula, we will get it as if you substitute these values, we will get it as delta L is equal to P is the common, so you take it as a common factor, and E is the common. We will get P by E is equal to L1 by A1 plus L2 by A2 plus L3 by A3. So delta L is equal to P by E into L1 by A1 plus L2 by A2 plus L3 by A3. If we had, then delta L is equal to, what is the P here? P is, value of P is 100 into 10 to the power of 3 divided by Young's modulus is equal to 2.1 into 10 to the power of 5. This is the value of Young's modulus. Now L1 is 200 plus 300 plus 200. This is L1, L2, L3 divided by A1 490.87 divided by 314.16 divided by 176.71. This is a different areas for different length. So that if you solve this, we will get delta L is equal to 1.18 mm. This is the change in length. This is the change in length for different cross sections of bar. Here our intention is to find out what is the total change in length. So here given as another extra question here given in this problem, so that you need to find out what is the strain energy they asked here. What is the strain energy stored? So that strain energy is equal to energy stored. Energy stored. We have energy stored U is equal to half into P into delta L. Half into P into delta L. Half into P into delta L. This is the strain energy stored. So that U is equal to half into P 100 into 10 to the power of 3 into delta L is 1.18. We will get it as strain energy as 59,000 Newton millimeter. This is the strain energy stored in the bar. This is the strain energy stored in the bar. U is equal to 59,000 Newton per millimeter. So that let us take on the next problem. Here given steel rod of 2.5 centimeter. Here given steel rod of 2.5 centimeter diameter is subjected to forces as shown in the figure. Here 2.5 centimeter diameter is subjected to forces here as shown in the figure, and we have to find out what is the total elongation of rod. Total elongation of the rod, and here also given as E is equal to 200 kilonewton per millimeter square. In this case, here this figure is given, having the here in this case we have the same diameter. Here we have the same diameter, that is 2.5 centimeter diameter, so that here the sketch is given like this. Here the system of forces are shown like this. $50 kilonewton, here 60 kilonewton, this is 10 kilonewton, this is 20 kilonewton. So in this case we have to find out what is the total elongation. Here point A is given, A, B, C, D, and length is given 1.5 meter, 1 meter, and this is 2 meters. Here length of each block is given and system of forces is given. Here we need to find out, here given thing is the diameter is given, that is equal 2.5 centimeter, that is 25 millimeter, and E is given, E is equal to 200 into 10 to the power of 3 Newton per millimeter square. E is given, and L1, L2, L3 is given. L1 is 1500 millimeter, we can write it as directly. L2 is 1000 millimeter, and L3 is 2000 millimeter. This is the given data. Here system of forces is different. In last problem, here system of only at one place we are applying the force, so that the force at every block is same. In this case, system of forces applying is different, so that we need to analyze what is the forces applied in all the directions. Suppose if you consider the block AB, if you consider the block only AB, here given as a 60 kilonewton. So question is, here how much load we have to apply for an equilibrium? We have to use here equilibrium equation, so that if this side is acting 60 kilonewton, if this block should be in equilibrium, same for 60 kilonewton should act in the opposite direction. See here 10 is given. If take that 10 is a positive thing, so that 20 kilonewton is acting in another direction, so exactly opposite to 10 kilonewton, so that we can consider negative sign for this, and 50 kilonewton also is acting opposite to 10 kilonewton, so that we will get minus 50, so automatically it will get 60. That means that this block is exactly acting, this block is in equilibrium, so that two equal forces are acting in the of same magnitude acting at different direction. So that here we will get P1 as 60 kilonewton. We will get P1 as 60 kilonewton, and L1 is 1500 millimeter. So then exactly in the second case, if you consider a block BC, here 10 kilonewton and 60 kilonewton are acting in the same direction. 10 kilonewton and 60 kilonewton are acting in the same direction, so that 60 plus 10 we will get it as a 70. 60 plus 10 will get it as 60 plus 10 will get as a 70 kilonewton. So that in the same case in this side 20 kilonewton and 50 kilonewton are acting in the same direction. So that 20 plus 50 we will get it as a 70. 20 plus 50 is 70. So here two forces of same magnitude are acting at different direction. Here we will get length as 1000 millimeter. 1000 millimeter. Here P2 is 70 kilonewton. Here P2 is 70 kilonewton and L2 is 1000 kilonewton. Here P2 is 70 kilonewton, L2 is 1000 kilonewton. If you consider a block, CD, if you consider a block CD, here two forces. Here see this 50 kilonewton acting this side. Here 50 kilonewton acting this side. In this case, exactly 20 kilonewton is acting this side and 10 kilonewton and 60 kilonewton acting in the other direction. If you take 20 as a positive, you have to take if you take 60 kilonewton and 20 kilonewton exactly acting in opposite direction, so that if you take this is going exactly in the direction of 50 kilonewton, so we have to take negative sign for this side, so that you will get minus 20 plus 60 plus 10. Minus 20 plus 60 plus 10, we will get it as 50 kilonewton. We will get it as 50 kilonewton, so that P3 is equal to 50 kilonewton and L3 is equal to 2000 millimeter. Here system of application of forces is different, so that we have to analyze, if in this type of problems we have to analyze the blocks separately. Maybe any types of system of forces is given, we have to analyze separately and we need to find out what is the change in length. Now we know that L1, L2, L3, P1, P2, P3, so that we can directly substitute in the equation. We can directly substitute in the equation. Delta L is equal to here cross sectional area is same. So that both here A1 and E are both remain same. So that we can take A and E as common. So that P1 L1 plus P2 L2 plus P3 L3. If we substitute the values of P and E, area is 490.87 into E is 2 into 10 to the power of 3. If you know substitute values of A and E, 60 into 10 to the power of 3 into 1500 plus 70 into 10 to the power of 3 into 1000 plus 50 into 10 to the power of 3 into 2000. If substitute these values, we will get delta L is 2.64 mm. Delta L is 2.64 mm. This is the total elongation. The answer is positive. That means it is increase in length. Okay, thank you.